Thank you for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Hello, everyone. Thank you for joining us today, and welcome to today's webinar from our Standards Activities Board series, and today's presentation from the IEEE 802.3 Ethernet Working Group. My name is Scott Levine. I'm the membership manager of the IEEE Computer Society, and I will be your host and moderator today. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded, and you can ask any question you want in the Q&A box you see on your screen. The speakers will answer as many questions as possible. When submitting a question, please reference the slide your question refers to, and you will get a copy of the slides and the recorded webinar will be emailed you within 24 to 40 hours after this webinar concludes. Ethernet is important to any of us. The 802.3 working group, which is managed by our Society 802 Landman Standards Committee, focus on developing these cutting-edge standards for Ethernet. You'll hear lots of useful and practical applications about 802.3, such as those used in automation and process control industries. In this webinar, we'll have a live discussion with our speakers, John D'Ambrosia and Kent Lusted, about this topic. Our first speaker today is John D'Ambrosia, who is a distinguished engineer with the Datacom Standards Research Team at FutureWave Technologies, a U.S. subsidiary of Huawei. John has over 25 years of supporting industry standards development. John is currently the chair of the IEEE P802.3dj 200 gigabit per second, 400 gigabit per second, 800 gigabit per second, and 1.6 terabit per second task force. Previously, John has chaired the IEEE 802.3 task force that developed 400 gigabit Ethernet and 100 gigabit Ethernet, 200 and 400 gigabit Ethernet, as well as the 800 gigabit Ethernet. Additionally, he chaired other 802.3 task force, the 802.3 New Ethernet Applications Ad Hoc, and is also a member of the 802 Landman Standards Committee. In addition to his many roles within IEEE 802, John is one of the founders of the Ethernet Alliance and served as chairman from 2011 to 2019, and is currently serving as an advisor to the board of directors. Our next speaker, Kent Lusted, was most recently a principal engineer within Intel's Network Edge Group. He won an Intel Achievement Award in 2002 for delivering the world's first gigabit Ethernet controllers. Since 2012, he has been an active contributor member of the 802.3 leadership team, and Ken is currently the electrical track chair of 802.3dj task force. Outside of his work, Ken enjoys time with his family, playing in the snow and exploring rural America. So John, without further ado, I know you and Ken have a lot to go through, so I'll turn the floor over to you.
Thank you very much, Scott. Good morning, good afternoon, good evening, wherever you are in your part of the world today. We're going to give you an update on the 802.3dj task force and our journey to 1.6 terabit per second Ethernet. Before I get started, I will point out, in accordance with SA Standards Board bylaws, that we are not here as representatives of IEEE today. So anything that you hear us say today is our opinion of what is going on and not a formal position of the IEEE. As Scott already indicated, I will be the presenter. I'm the chair of the task force, and Kent Lusted is the chair of the electrical track, as well as the heart and soul of the group. He keeps us all in line. So, Kent, I'll ask you to keep us in line today again, as you normally do. Before I get started, I want to point out to everybody that the standard that we're talking about today was just updated last night, the latest draft, and it's 850 pages. So we're not going to go over 850 pages today. We're going to try to give you an update on where we are. If you are unfamiliar with the standard today, I would suggest that you go and look at our webinar from last year, where we talked about the journey to 801.6 terabit Ethernet at the link right there. It's in the library, and that will get you up to speed on where we were prior to this webinar. But today we want to kind of just focus in as much of the time as possible to give you an update on what is actually happening in the standards development and what is going on. So let me start with a brief introduction. Currently, prior to 800 gig and starting this project, the 200 and 400 gig standards were introduced in late 2017. Shortly after that, we initiated an effort to do a bandwidth analysis study, and at the end of in 2020, then the analysis that we did highlighted that there would be a need for something greater than 400 gig Ethernet. And when we looked at the forecast, what we saw was that 800 gig was coming on us really quick, and we would need to go beyond 800 as well. This led to a bifurcated approach to going beyond 400 gig. The 802.3df project developed 400 gig solutions and 800 gig Ethernet and introduced it into the ecosystem. And those solutions were all based on 100 gig signaling. There was also then the 802.3dj task force, which is developing 1.6. It'll be a new speed for Ethernet. But then we're taking those same technologies that we're going to use to develop 1.6 and applying them to 200, 400, and an 800. And we'll wind up providing those speed with higher density, lower power solutions. And those solutions are going to be based on 200 gig or greater signaling. And we'll go through that real briefly. The current status right now is the 802.3df standard was approved earlier this year. So that is now out. And people are deploying 800 gig Ethernet based on the DF standard as we speak now. But today's webinar is about the 802.3dj standard. And that is scheduled for approval in the second half of 2026. So we still got a long way to go, but we're going to give you an update on this. And I imagine in the future we will give you another update. All right, so when we talk about Ethernet, we're not talking about a single solution. And when you develop a new rate of Ethernet or a new family of solutions, you wind up looking at the complete ecosystem. If we look at the box-to-box connections for Ethernet, we've got server switches, you've got the leaf and spine, you've got the routers, you've got data center interconnects, you've got twin axle copper cable, you've got multi-mode fiber, you've got duplex and parallel multi-mode and single mode fiber, and then you even go out into DWDM in some cases. That is the ecosystem that Ethernet and any new project is always asked to address. So let's go into this a little bit. Okay, so first of all, the DF project, I'm touching on this just for a real quick introduction because it is important to the evolution of what happened with DJ. So you'll note that the 400 gig matrix is fairly blank. It's really only introducing the 2 kilometers. And the reason why was all of those other solutions, the chip-to-chip, the chip-to-module interfaces, the backplanes, copper cables, multi-mode, single-mode fiber, they were already developed. They were all developed using 100 gig signaling technologies, and you had solutions based on 4 lanes that delivered 400 gig. Now you'll note in the 800 gig column, everything says over 8 pairs, 8 by 100. Okay, so we basically took the solutions at 400 gig and grew the number of lanes from 4 to 8 in order to then provide 800 gig Ethernet. And this was, as I said, already based on mature technology. The noted standards below were already approved and ratified, so it was a fairly easy project, all things considered, compared to what we're now dealing with DJ. But the important takeaway here is that the width of the interfaces that we were using in the solutions has now grown wider. It used to be 1 pair or 1 lane and 4 lanes. Now we go all the way out to 8, and it becomes an aggregate story. Now, what do I mean by that? This chart's a real easy way to see this. You can see we have on the left-hand column the different rates: 200, 400, 800, and 1.6. And in general, all the signaling that we're developing here is 200, and then we're developing some 800 for coherent. But we're now addressing that full ecosystem that we talked about before. The different interfaces, backplane solutions, copper cable solutions, single mode fiber for 500 meters all the way up to 40 kilometers. Multi-mode fiber is not part of this project, though I envision that will be happening in the near future. It's also important to note that when we talk about the road to 1.6, we're really talking today about supporting 1.6 terabit up to 2-kilometer reaches over single mode fiber. Remember, this project was started in 2020 and 2021, so at that time, we thought 800 was going to take us for quite some time, and 1.6 would be addressing the early adopters, which we envisioned as the data centers. Okay, so we're going to focus in primarily on that stuff today, though we will talk about the general overall architecture that will allow us to then support these other reaches and distances. Okay, so moving ahead, let's talk about one of the big things, and one of really the heart of the project in my mind is the use of forward error correction, FEC. Let's start first of all with the general architecture overview. Okay, now anybody who's familiar with Ethernet has seen these block diagrams. They're very useful for us when we start to talk about different things and different approaches. Normally we'll start from the top and work our way down, because that would be the physical layer starting, right below the MAC and going down through those different layers. But I want to start today from the medium and work our way up and talk about the differences that we see in the DJ project. Okay, so first of all, there's the medium. So this would be the copper cable, the twin ax cables, the multi-mode or single mode fiber, whatever we're addressing down there. Okay, and I just showed all of those. The MDI is the connector, the interface, if you will, between the medium and then what we call the PMD sublayer. Now the PMD, or physical medium dependent sublayer, is what interfaces with the transmission medium. And it's really what's responsible for driving the signal across that medium. Clearly we have different mediums, so we have different PMD layers. So we have a PMD that is useful for the backplane, another PMD for the copper cables, others for the different reaches of fiber, as well as the parallel fiber approaches. Okay. Then we have, going up from the PMD, the PMA sublayer. And the reason why I'm going upwards is because it's easier to explain the variations. So now, in the case of the PMDs, there's different variations based on the mediums. In the case of the PMA, we actually have 2 PMAs. One is based for those signals that are doing 100 gigabit per second, and it's not just really the AUIs, but clearly, at 800 gig, I've already shown you that we have PMDs that are based on 100 gig signaling from DF, and we'll have PMDs based on 200 gig signaling for DJ. And then we have the 200 gigabit per second based PMA. And the difference between the two of these is when we're talking about the 100 gig signaling, when we do muxing, and that's where you combine bits, you do it on a bit muxing basis, a blind bit muxing. But when you do it at 200 gigabit per second, you're really doing it on the FEC symbol words. So there's a difference here. And it's these two PMA sublayers that are working together that allow us to address 100 gig solutions and 200 gig solutions and make them interoperate with each other. So you know what you're trying to deal with. You can combine these things as you need to. The next thing we have is the PCS. And the important thing with the PCS is, yes, it does all of the coding, but it is also responsible for the FEC. Now, the reason why this is so important is because this project doesn't just have one type of FEC. And that's very, very important, all right? Then you go up into the RS sublayer and the MAC. Before we move on from this drawing, I want to point out what's called the PHY, all right? And the PHY is the combination of this PCS to the bottom of this PMD sublayer. And that will become important in the next slide, where I show you architecturally how we move things around. Now, there are 3 different FEC schemes that the DJ architecture actually enables. And I'm going to go through those in a couple of slides to explain this. In the case of the first column to the left, we have something that's called end-to-end outer FEC. And in this what we call PCS1, you'll see that there's something called FEC-A. So there's a FEC code that's applied here, and it's a singular code. And it will cover everything that goes throughout the link. In the next column, you have something that's called concatenated FEC, and you have an inner FEC code. Now, in this case, you'll note there is what's called FEC-A, and it's the same FEC-A, same PCS as what was in the first column. But within the PHY itself, we then apply a second FEC code, an inner FEC code, if you will. And in this case, that FEC code is applied without terminating the first FEC code. So think about it as like a multiplication effect to get additional signaling gain to solve the problem that you're trying to get to. Finally, then we have what's called the segmented FEC. Now, in this case, this PCS1 is actually, if you will, set up to be something else, a different sublayer, if you will, something what we call the DTE XGXS. And this MII layer up here at the top is essentially extended, all right? And it's pushed down all the way through here, and you can see virtually it comes at this point right where the mouse is, below where the FEC-A is. Now, when you go across this MII, your data is unencoded. Now, this is very important. So what's happening here is the FEC-A that we started with this, PCS1, which is now this DTE, comes down. It's covered, sent over what's called an AUI. Those are the interfaces that we were talking about before. And then it's then terminated, and you now have an unencoded data stream, essentially, that goes across here, and a new FEC. So it's been terminated. The FEC-A is used to get across some PCB traces, and then it's terminated, and then you initiate a new FEC. Now, there's a lot of stuff going on here that's very subtle. Let me kind of just draw a line in here to explain and provide it in a different perspective. Let's say we have a big chip, and we're going to cross that chip to a circuit board and go into an optical module. All right, so above the line is my big chip. Below the line is my optical module. Now, what you see happening here is the PHY essentially goes across here, across the board, and goes into this optical module, and there's nothing happening with the FEC, okay? This whole top part stays the same, so you have commonality, which is great, right? Because we want to drive volume to drive the cost down. We don't want to have different things happening here. In the case of the concatenated, you do the same sort of thing, and then you apply that inner FEC inside the module, and there's nothing ever terminated here. It's just multiplied like we talked about before. But now in the segmented, what we've essentially done is what I talked about before, the PCS. We've pushed that PCS into the module. So you come down through out of your big chip, you're encoded with this FEC-A, you go across your electrical interface into the module, you're then terminated inside the module. You come back and your unencoded data, and then you introduce the new FEC. All right, now there's a few things else that are happening here. In the case of the end-to-end outer FEC, this is the lowest latency. That's very important for very near applications. You know, the closer you are, the less you have propagation on the medium, the more latency becomes very sensitive. Then you have concatenated. This adds a little bit more latency. And then you have the segmented. And in the case of segmented, you're adding latency and you're adding power. So by providing a flexible architecture, you can tailor it so no one solution has to share the burden of everything. All right. So in the case of the end-to-end outer FEC, I don't have to support a segmented FEC if I don't need it in that case. I can provide a module that doesn't have this segmented FEC in it because I'm only going to try to drive this, in this case, 500 meters. But if I really want to go 20 or 40 kilometers, I know I'm going to need that extra FEC. And I know latency isn't going to be as big of a problem. So to put it in perspective, if I'm looking at, I think 800 gig, the latency of comparison between the end-to-end and the segmented is twice the latency of the end-to-end. Okay, and that's just going in this stack. That's not including the medium and all of that stuff. So we're just talking about this stuff going down from the MAC all the way down to the medium. So you're looking at roughly, I think it was like 65 to 130 picoseconds between the two. So 65 for the end-to-end and 130 for the segmented as an estimate. So that kind of gives you an idea and description of what's happening there. Now, to put it in a more visual sense, you know, let's say I have this topology right here, and I'm going to do a end-to-end FEC. So this FEC code is covering everything, and it corrects all the errors in this sense. If I then go to a concatenated, I've got the FEC code A, once again correcting all of the other errors, but really this FEC-I that's correcting most of the errors across the medium. And then finally, I have the segmented, and you can see it's terminated, right? So you have a FEC that covers the AUI interfaces on the circuit board, another FEC that covers the medium. And in this case, we're really talking about for optics that are coherent-based optics and going 20 to 40 kilometers. And then at the far end, you terminate that FEC again, and then you have another FEC, FEC-A that covers the chip-to-module and chip-to-chip AUIs on the far daughter board. Okay, so that's more of a simple visual to try to help you understand what's going on with the different FECs. To put it in perspective, and why do we need all of these? Well, if you think about it, we're really going from millimeters on a circuit board out to 40 kilometers over single mode fiber. So the end-to-end FEC covers everything from inside the box to 500 meters. We have two types of concatenated FEC codes, one that's covering, one that's covering the 2 and 10 kilometers based on IMDD optics, which is the by 4. And then we have a what's called the 800G base LR1, which is a coherent approach that's using a concatenated FEC. And then we use the segmented OFEC. So that's the OFEC is that intercode FEC that we were talking about to go 20 and 40 kilometers. All right, here is a simple summary. If you just follow across here, you can see there's an end-to-end FEC, and this applies to these PHYs. It's an RS Reed-Solomon 544-514 code, 5.8% overhead. The signaling rate is 106.25 gigabaud, and it's a hard type of decoder. There is no second FEC. In the case of the two concatenateds, here's the approaches here. You just can read across and go there, and that shows you the different things. And you can see that there is more overhead when you're going to the coherent approach, going to the 10 kilometers. And then for the segmented, you have even more overhead, but you're also going further distances, 2 to 4 times the other differences. Please note, we've kind of had some differences and changes here. The FEC 1 that I'm referring to is the FEC A on the prior slides, and the FEC 2 is either the FEC I or FEC B, depending on which PHY that you're actually looking at. Right? So that kind of gives you an overview of what's happening with the FEC. At this point, I'm going to turn things over to Kent and let him talk about all of the different PMDs. Kent?
Great. Thank you very much, John. Good morning, good day, good evening. Thank you for joining for this IEEE Computer Society update on the IEEE P802.3dj project. I'll be talking specifically about the PMDs. Now, the PMDs at 200 gig per lane are a critical part of the project work in 802.3dj. And the PMD specification complexity itself continues to grow and grow and grow substantially from prior rates. When we look at the complexity from 25 gig NRZ to 50 gig PAM4 and from 50 to 100 gig PAM4, there's a jump in complexity. Here, we're seeing a substantial growth. And this really is because of the overall challenges with the channel and the solution and looking at it holistically. The key to success here is the optimization of PMD characteristics, in that every little bit matters. The analogy I use in this space is finding pennies in the sofa. Every little cent matters. And there's optimization of these PMD characteristics based on media type, as well as by reach, and we'll look at the implications of those. Another trend here is that the PMDs at 200G per lane, it's a matter of finding the best solution for each particular type of PMD in order to yield the maximum performance for a particular use case, whether that use case is a chip-to-chip connection, a chip-to-module connection, copper cable connection, an optic end-to-end link. It's a matter of being able to use every dB of loss as effectively as possible. In this particular project, there's equal importance between electrical interconnects and optical interconnects. And as John showed in the previous slides, it's a matter of using the right FEC architecture and solution architecture in order to accomplish this task. For example, on the top, shown in this picture here, you'll see that the top part here with a copper link has a pretty simple interconnect. It's a copper cable or a backplane link. And generally, these are passive devices, passive interconnect. On the bottom here, you'll see is an example optical link. In these cases, we have electrical interconnect going to an optical module, which converts it to light, and then from light back to electric across the PCB to the end host. And so the approaches that are taken in the PMDs is trying to find and leverage maximum commonality where there is, and where there is a need to differentiate and take a different approach, applied in order to use each dB of gain or each bit of margin as effectively as possible. Looking at all the different objectives, as John had shown on previous slides, but mapped a little bit differently here, you'll see that we have here on the vertical axis the Ethernet rate at 200, 400, 800, and 1.6T. And then you'll see that we have this broken down by columns here, each of the different interface types: an AUI, an attachment unit interface, the backplane, the copper cable, 500 meter single mode fiber, 2 kilometer, 10 kilometer, 20 kilometer, and 40 kilometer. Now, I've taken the same information that's been provided and again provided a little bit different viewpoint, and that you can see that there's 3 natural groupings of interconnect types. There's the green over here on the left-hand side, which are the copper interconnects. In the middle, you'll see that there is a red box centered around the IMDD optics. And then you'll see over here on the right-hand side, the coherent optics. So in this case, it's a matter of reach mapped across different types of interconnects, copper or IMDD optics or coherent optics, finding the right type of solution for the given reach by rate. If I take this same graph and I look at it a little bit differently now, by looking at it from modulation type point of view, it's the same graph, but you'll see that there's two groupings in this case. You'll see on the left-hand side highlighted in red, there's a grouping that use PAM4 modulation. This is the best type of modulation solution for these particular types of mediums. And then on the right-hand side, you'll see highlighted in green, QAM16, specifically for the coherent stuff, that again is the best type of modulation available for that technology. All right. So we've seen it looked at by reach and grouping. We've looked at it here now by modulation, but we can also now look at it to the next step for the optic side, IMDD specifically. How does the fiber interconnect look? Highlighted in the green at the top, you'll see that there are a group of connections that are duplex fiber or part of a parallel single mode fiber bundle, such as a breakout case. Okay. That's highlighted in green. Then you'll see highlighted two bands in yellow here and here, in which the solution type is a single wavelength over parallel fibers. So it's the same type of laser, just using different individual fibers to reach its destination. And then last but not least, on the right-hand side, you'll see WDM over duplex fiber, in which multiple wavelengths are being used across a pair of fibers in order to reach the destination. Again, same set of objectives, same rates, but looking at it through three different lenses. One is by looking at the class of interconnect, copper, IMDD versus coherent, then looking at it by reach, and now looking at IMDD specifically, the different type of fiber interconnect. As I've alluded to in the previous slides, we're leveraging a number of different modulation technologies. And the modulation type is optimized for the particular kind of medium and its reach. And this enables higher performance with lower cost. Examples on the right-hand side show the modulation that's being used. On the top right, for copper and IMDD optics, we're using PAM4, so 4-level modulation, gives us 2 bits per symbol. And then for the coherent optics, we're using 16 QAM, which gives us 4 bits per symbol. Now, using more complex modulation allows us to increase the data rate without increasing the signaling rate, but it also does have some consequences with implications on the FEC, forward error correction methodology or architecture that is adopted. As John highlighted, we are using a helper FEC, the FEC I, or a different FEC, FEC B in some of these cases. All right, well, let's talk now about continuing to find margin. One of the principal tools that is used in the electrical domain is COM, the channel operating margin. And there's this particular reference model that's used in this part of the specification. In prior IEEE 802.3 specifications used a DFE-based reference receiver architecture for the specification of these electrical channels, as designated in the channel operating margin. Now, that model approximated product implementations and expected technologies for rates less than or equal to 50 gigabits per second per lane. So 50 gig PAM4, 25 GNRZ, 10 and down. COM was a good model when using a DFE-based reference receiver architecture. But what we saw in industry was that at 100 gigabits per second per lane, implementations shifted to ADC DSP-based solutions. So there was a disconnect between what the specification called out for a reference receiver architecture versus what the implementations were. And in this particular case, for 200G per lane, a new COM reference receiver architecture was adopted. This is a feed-forward equalizer with a one-tap DFE that represents a more realistic ADC and DSP-based implementation. Now, this particular architecture change as well enables the support for maximum likelihood sequence detection, MLSD model, which is another tool that we're using in the toolbox to help find margin to make the channels work. Finding margin, the package was another item that was explored. no longer is there a one size fits all, and that the overall package size itself varies. It depends on whether you're building a large switch or router chip, whether you're building a large CPU or GPU, or whether you're building something small like a retimer or a companion ASIC to go inside of an optical module. And so in this case, we needed to look at a couple different approaches and recognize that one size no longer fits all. And the differences between the shortest package trace and the longest package trace within a given package, whether it's a large one or a small one, becomes much more significant when you get to larger packages. So as a result, we ended up with two types of packages. We have a Class A and we have a Class B. Class A is loss optimized, Class B is radix optimized. And you'll see that there's a difference in the package insertion loss allocation of approximately 3 dB. Okay, and this will come into play later on when we look at more of the copper interconnects. Now, finding margin in terms of the copper cable links themselves. Previous IEEE compliant definitions of copper links did not allow the reallocation of loss across the link. Now, what does that mean? I'll have an example on the next slide, but what it really means is that both copper cable hosts on each end are assumed to be equal in terms of loss and capability. In this project, the asymmetric host was introduced. Now, the host budget for each end of the link may not be the same. It can be the same and be symmetrical, or it can be different. And we'll look at those in the next slide. Now, this asymmetric host architecture is well known and is being deployed in the market with prior signaling rates, but this is a way to bring it into the standard space as a tool in the toolbox to help find margin. Why is this important? Because the loss is not equal on each end of the cable, and that depending on a particular implementation, whether it's a small NIC card or an AI accelerator, there may be shorter PCB traces and smaller packages compared to, say, a giant switch or router that has a very large package, very long routes to corner cases. And this particular approach enabled a wider range of low power, low cost links. So let's look at some pictures. Here in the top, you'll see the standard use case. This is what has been typically defined in the specification, prior specifications. And you'll see that we have a symmetric host loss on the left and symmetric host loss on the right is what is assumed. And this can be implemented, for example, with a short package here, with a long package, or excuse me, a long host, or a high loss package with a short host. And this is generally assumed on both cases. Now, what 3DJ enables is more use cases, such as the second case, in which I'm able to take loss from one end of the link, say the right-hand side, which may represent a NIC card or an accelerator, and move that loss to the left-hand side over here to be, say, a switch port. Okay, that allows you to keep the same length of cable, but allows you to use more ports on the switch. Now, the bottom case is the case in which we're going to take loss out of both ends of the solution, okay, on the left and on the right, and we're going to put it into the cable in order to have a longer interconnect. Now, this may be interesting for NIC to NIC case, or interesting for accelerator to accelerator type of connection, right? So again, trying to maximize the solution space, find where there's margin, and apply it into the solution. In the backplane case, which is the KR, you'll see that these different host classes of packages become an important part of the mix as well. Depending upon the backplane host, transmitter, and receiver, whether you're using a Class A package or a Class B package, determines exactly how much channel insertion loss is allowed. Okay, in the past, you had one assumed host loss on both ends, which gave you one assumed channel loss. Now, it's more a matter of understanding the co-design of the channel with the targeted packages on each side, as well as the design of the package and the solution in conjunction with the channel. So it's a two-way street, if you will, right? There's synergy that goes between the two of them. So in the compatibility matrix at the bottom, you'll see for a given supported channel loss, you can see which transmitter class A and B goes with what receiver. So again, calling attention to industry implementers and operators that there is even a tighter collaboration and connection between the channel and the targeted package. Now, finding margin as well in order to get to the front panel for a pluggable optics module. In the past, the standard and the specification and the participants have been mostly focused on traditional PCB trace type of architecture, okay, in which an ASIC with a package goes to some PCBs that may or may not have a retimer here, that then goes to a pluggable optic module that has a laser or E/O inside. Well, we recognize that with the new approaches, new technologies, and the availability to, and the need to find more margin, we had to look at alternative implementation approaches. And as a result of that, you'll see 3 new categories that are really being embraced in the development of the specification. First is in-box cabling, in which this PCB portion of the host is being replaced with an in-box cable. You're also seeing some support and consideration for the case where the optical engine moves away from the front panel pluggable connector inside the box to be near the package or even all the way on the package. These are all chip to module AOE use cases, okay, supporting in-box cabling, near package NPO, or co-package CPO. Furthermore, for finding margin, link training for copper was another aspect that was looked at. Now, link training itself has been around for a number of generations of products and continues to be a key tool available for improving the performance of copper cable links. In this example, again, you'll see the host through a connector over a copper cable to another connector in the host. Now, the link training continues for copper cable and backplane links, and the link training messages are exchanged between system A and system B host. Now, one of the things that was modified in link training in order to get a little extra margin is that we've introduced some new PRBS, pseudo-random bit sequence patterns, to improve receiver calibration for the channel impairments. As you can see, the channel is a strong predictor of performance and margin of the system. So we're adding tools in the copper cable space in order to be able to assess all these different impairments that may be in a system in order to find the best possible performance of the solution. Well, not only are we doing link training here on the copper cables, but new for 802.3dj is the use of link training for optical links. Now, link training actually occurs in 3 different places now, unlike on the previous slide, in which the solution is entirely passive from the host on the left to the host on the right. In the case of retimed optics modules, there's now segments. And what you'll see now is that we have link training brought into the optical domain in 3 locations. First, I'll call your attention to the middle segment, in which the optical to optical connection itself supports link training. There's a link training protocol that runs on it, and information is exchanged in order to bring this link segment up. But I'll also call your attention that the electrical interconnect between the optics and the host on the right and the optics and the host on the left itself has link training. So in this case, that's electrical link training. So we've added link training between the host and the local optic module, as well as the optical modules themselves. Now, what this particularly provides is an orchestrated link establishment between the hosts, in which now, for the first time, there is a standardized mechanism in which you can coordinate and orchestrate the establishment of optical links, such that you know when link training is completed on the optical interconnect, as well as when it's been completed on the electrical interconnect on each side. Okay. This is an important way in order to establish the link in a manner in which there is a sufficient amount of margin and a way to maximize our performance. Okay, so let's look now at the optical channel itself. So we've talked about the host, we've talked about different host architectures, we've talked about finding margin in passive copper cables, we've talked about the implication in backplane, we've looked at link training, but another stone that needed to be turned over was the optical channel itself. With 200 gigabit per second IMDD PAM4, we found that the fiber chromatic dispersion itself starts to have an impact on the reaches, around 10 kilometer. Okay, so now this optical fiber itself has some impairments that really need to be considered at this rate. As a result of this, there was a reevaluation of the worst case fiber specifications in order to determine, is there relaxation or are there changes in methodologies, is there changes in approaches? Let's revise the model. This work is ongoing with collaboration with the ITU. It has involved a significant amount of data collection from industry partners, and it's also bringing to the forefront new ways to visualize and think about and process the data that is consistent with current cabling approaches, exactly how fibers are deployed in real deployments in the enterprise telco cloud scale environment. Now, the outcome overall here is we're expecting a revised chromatic dispersion spec that will allow simplified transceiver design, finding that right balance of cost and power, but it doesn't affect the usage of any of the existing fibers and cables, really understanding what's already out there and how they can be utilized to find the appropriate amount of margin for optical receivers. So to summarize here, on the optical and the electrical PMD side, what are the optimizations that we've looked at? We've talked about here on the top, the copper link case. We've talked about the packages, the Class A versus the Class B package. We've talked about the assumptions in the host loss itself as to whether this is a symmetric host or an asymmetric host, as shown here in this particular picture. We've talked as well about how the loss allocation can change the length and the loss of the cable. We also talked about the copper link training itself using a new PRBS training sequence in order to find improved margin. We've talked about the reference receiver itself being shifted to align better with expected implementations. On the bottom, for an optical link, again, we're seeing the same change in the package. We recognize as well that these hosts over here may be in-box cables, they may be near package optics or co-package optics. We're seeing that there is link training now going on between the host and the module. There is link training going on over the fiber, as well as the fiber itself is a revised model. And reference equalizer has been improved as well. So these optimization of these PMD characteristics, while it seems like a lot, it is, but each one of these gives us a little bit of margin that in sum is enough to make a substantial difference. All of these lots of little bits add up. Okay, and with that, John, I think we go to our conclusion.
Thank you very much, Kent. And I would say we're working on roughly 40 minutes, so we're doing really good, but we've only touched on a small portion of the specification. As I said, it's 800 pages, 850 pages as of right now. So I think there's really two ways that we need to look at this. First of all, what is this project bringing to the market in terms of new Ethernet solutions? As I said already, the DF standard was ratified earlier this year. People are deploying 800 gig today based on 100 gig signaling technologies that have been out in the market for a few years at this point. DJ is developing a lot of fundamental technologies here. So 200 gig electrical signaling for chip-to-chip, chip-to-module, backplanes, and copper cables. It's also developing all of the optical signaling technologies for these different mediums, as well as the related testing, which is a very important part, especially with the coherent signaling that we're touching on. We're anticipating that the standard will be ratified in the second half of 2026. We're making a lot of really good progress at this point. If you want to find out more about the state of the project, you can go to the homepage that I've listed there and the reflector. And please note the reflector URL is correct. So if you want to join this project, you can join by going to that portion right there. But there's a second part to this, and that's all of the tools that this is now adding into our Ethernet toolbox. Kent, why don't you do a summary on the toolbox improvements?
Certainly. Thank you, John. Okay. So adding tools to the Ethernet toolbox. As John and I have provided for you today, an overview of the multi-FEC capable architecture. We have moved from just a single FEC architecture to one in which there's an end-to-end FEC, a concatenated FEC, as well as a segmented FEC architecture, and an architecture that supports all of those. We've also touched on the symbol muxing PMA as a way to help break these errors up into ways to improve the overall margin of the link. For 200 gig electrical and optical signaling, we talked about changes to modulation. We talked about the implications that it had on the channel optimization in terms of the electrical interconnect for copper cables and backplanes, link training, et cetera. We talked about the channel optimization from the optics and the improved optical fiber model. And we talked about 800 gigabit per second coherent signaling and how coherent is now much more prevalent than it has been in the past in the data center reaches. We talked about link training. I just mentioned that a minute ago. Again, link training is a tool in the toolbox that is expanding from the copper interconnect space into the optical and the retimed optics space in order to be able to provide those improved margins. So those are all tools in the toolbox that will continue to be used in order to help find the margin in the system in order to improve the performance, the reliability, and the solutions available in the market. Okay, John?
All right. Well, Kent, thank you very much. And with that, Scott, we'll turn things back over to you.
Thank you, John. Thank you, Kent. That was a great presentation. A lot of information, as you said, would be delivered in there. We got a couple questions, so let's just jump straight into those. First question from Martin. He asked, will 1.6 terabit bring about PMA6 or PMA8 modulation?
PAM6 or PAM8 modulation. Great question. Great question, Martin. I'm gonna, Ken, if you don't mind, I'm gonna start with this and then I'll leave it to you to add on to it since you're more of the electrical whiz than I am. Martin, as with any generation of Ethernet, there's a first generation and then there's always a follow-on generation. If you look at 100 gig Ethernet, for example, the first interfaces were 10 by 10, then they went to 4 by 25, and then they really jumped to 1 by 100. And I think 2 by 50 was in there for a little bit. So there were multiple generations in there. So when you ask in your question, will 1.6T bring on PAM6 or PAM8? I think the question with this first generation is no. We've shown you now that we're going with PAM4 modulation in this first generation for the links that we're looking at. But when you start to think about other PMDs that may get added or next generation higher density, then yeah, possibly when we start to look at needing a denser solution, right? It's always an idea of, oh, let's go faster. So, the physics are getting such though that going faster, it's not that easy, right? It's not a matter that we can just keep turning these knobs. So modulation is another way to do it. And by encoding more bits, that would be a potential way to look at that. So I think in a future generation of 1.6 or even really a future generation of 400 or a denser 800, we'll see that sort of exploration start to happen. And I'm already aware of some of those questions happening with discussions about 400 gig signaling. Kent, you want to add on to that?
John, I think you answered it quite well. When the project was getting started, there was a look at other modulation beyond PAM4, such as PAM6 and PAM8, as was raised in the question. And the answer was the channel, for at least on the electrical interconnects, was enough, had enough gain and capability in it that new modulations such as PAM6 and PAM8 were not necessary. Okay, that was a good question.
Excellent. So Martin also asked, how dependent is 1.6T dependent on 224 gigabit per second electrical link developments?
That's a really good question, and it's one of the ones that it's one of the things that we probably could have spent more time talking about is the interaction between everything. Trying to think, Ken, what would be a good slide for us to start with on that?
I think slide 10, John.
Slide 10?
Oh, I'm sorry, 11. There we are, 11.
11. Okay. So, no, I'm thinking like our BER stuff, Kent. So probably one that shows everything. Probably, I think.
Well,
20.
while you're bringing that up, I think one of the things I want to highlight is that within the scope of 802.3dj, you will see on slide 10 that there are some 100 gigabit per second per lane interconnects choices. There's a AOE 1.6T, AOE 16, and that, so there is a 100 gig solution, but almost everything else is based on 224, if you will. Now, that 100G per lane solution is there primarily to enable early test equipment development, but otherwise, the focus of the project is really 200G per lane. John?
Yeah. Yeah, thank you, Kent. That's a great point. We do have that 1.6 in there based on the 16 lanes by 100. But as Kent said, that's for test equipment. And I'm sure we can all agree that that would take up a lot of pins on a package, right? So it would really have a impact on the density one could achieve going into a switch. Now, Martin, I need to answer your question in this way, okay? So first of all, any implementation of the AUIs, the electrical interfaces, they're always optional. And when you ask the question about dependent on the electrical link development, I'm assuming that you're really talking about this part of the link, okay? And the reality is, you know, for what we've enveloped and developed, you don't have to implement the PCB version. It's optional. You know, it would be up to you to figure out how to do that, how you want to do that. But, you know, I think the reality is that not everybody is doing onboard optics at this point. You know, the onboard optics is an easy way to say, okay, do I really need that electrical link development to the same degree? And Ken, I'll let you touch more on that, but you see where I'm going with this. So I think in that sense, if you have the ability to do it, fine. It's your implementation ultimately that you control. There is another component that I do want to add in here, and that is this link. When we look at it in these three parts, we've had to budget the BER or the frame loss essentially across each of these portions. So you really need to meet what we call out for each of these. Okay, I hope that makes sense. So the link itself is highly interactive and highly dependent upon each other. You can't assume more errors on the PCB. You will break the link in the fiber portion at that point. Ken, I'll leave that one more for you to touch on then.
All right, so John, just briefly to kind of button this one up, when I look at, for example, this picture on the top, the general assumption around a copper cable or backplane link is that the whole solution has the same signaling rate, so it's 224 across all. But as you alluded to and described in your previous statement, it's the bottom section with the optics that actually allows you and provisions of the specification to use, for example, 100G signaling to the optics and 200G signaling over the fiber, then to 100G or 200G signaling. So in optics, retimed cases, things can be broken. So there is a dependency, but there isn't depending on the particular interconnect.
Okay.
All right, I think we've answered that one.
All right,
Yep.
great. We're at the top of the hour, but I think we'll do just one last question. Will 802.3dj be of interest to AI networks? I know AI is a big topic these days, so I thought this would be a good one to ask.
Great one to ask, actually, and to end with. I think the answer is yes, very much so. We have already, the DJ project, as you know, is part of 802.3, and we have already received inquiries and liaison requests from both the UEC and UAL organizations. And there's conversations going on between those groups. In addition, there has been some discussion in the industry already about the future of Ethernet and applicability to AI networks. There was a event that the Ethernet Alliance held, Technology Exploration Forum, back in October, that those conversations are now starting. So, you know, everybody wants Ethernet to evolve and apply Ethernet and all of its known benefits. You know, it works, power, cost, across the board. So I think if I were to pull out my crystal ball, I think 802.3 has got a very big target in its sight for the future of Ethernet. Ken, anyone add anything there?
Nothing I'll add. Well summarized, John.
Thank
All
you.
right.
Okay, Scott,
Excellent.
we're done.
Yeah, excellent webinar, you two, John and Kent. As I said, a lot of great information, and thanks for sharing for everything going on in the latest developments in 802.3 Ethernet. If you're interested in participating or contributing to standards activities, you can be part of the Standards Activities Board activities such as this one. Keep an eye out for ongoing calls for participation and ways to get involved. Being part of this community is an opportunity to share your insight with like-minded individuals like John and Kent from across the globe. You can visit computer.org, which is our website, to find information. I believe John and Kent had a link to the 802.3 site at the end of the presentation. I'm sure there's ways to contact John and Ken and other chairs to get involved that way from that site. Just a real quick program, you know, before we wrap up. The computer site is hosting 2 more webinars this month. On Monday, the 16th, our 2024 President, Jadika Athavale, will host her 4th and final quarterly town hall. Fresh perspectives, insights from new board members on their first-year journey. She's invited 4 first-time Computer Society Board of Governor members. They'll talk about this year's achievements and their perspective about the board and how it's changed over the past year. And if there's time, the second part will be about why they joined the Computer Society and how they got involved. And then 2 days later, on the 18th, Jadika will be joining us again to discuss her professional career development and her active contributions to both the Computer Society and the IEEE standards activities. She's going to talk about her career developments in engineering and across standards. Once again, I'd like to thank our 2 speakers for their great excuse me, update on 802.3 today. And thank you all for attending and joining us and help make a lively Q&A discussion. Thank you again and have a great rest of your day.